first, my brain did a goofy thing when we were talking about the sum and difference 2 cubes. Trying to think. I told you that it was not this, and then I wrote the rule down that way. I posted an announcement if you saw it. Thing we're factoring is a cubed minus b. And you get the pattern we did. I wrote down the wrong thing. I had down. Had it written down with the cube out here. That's wrong. I wanted to correct that. Now let's talk about Canvas. I think I have sorted out getting the assignments on the Canvas calendar, so maybe that'll help you up what's going on those. And the load will. Oh. Okay. If we can get the Wi-Fi to work, we'll look at it. Changes a couple things in Canvas, hopefully for the good. So one thing that does for us, we'll put the list of the assignments over here in the little to-do list. It goes over there. You go to the calendar for the course. Well, pop up there on the calendar, and you can click on those, and it'll take you straight to the assignment if you want that way. There's also one more place where they're showing up on calendar. Show up under modules as well. It makes that screen a little messier, but everything they've had assigned so far and the due dates. You can just click on those and it'll log you into WebAssign. One thing it does kind of make it a little messy. Not a big fan of it. In the grade book, you've got a row for every little assignment. The main thing to focus on, that's good. You can see if you missed one really easy there, but the main thing to focus on is it'll have your assignment score, and then anybody have problems from WebAssign we need to look at? Get one? 3 on which? Oh, okay. All right. Not mine. We can work as many or talk about as many as we need. One of the problems is how you really learn this stuff. The lecture just gets you ready to do the problem. So, which one was it on? Was it on the 2.2 or 2.1? One, okay. Head number 3. Mine may be a little different than yours. Similar. Uh-huh. Is it the one? Is it the part with the squiggly? Okay. Yeah. So on this one, if you're coming in 5 from the left, what it would ask on this one, our limit's not going to exist because we have that infinite oscillation. If you come into 5 from the right, you can kind of tell where it would be. And it would, on this one, it would be at 3. So it will exist coming in from the right on that one, but it would not exist coming in from the left. And since they don't match, the two-sided would. You're welcome. Has that infinite oscillation. Anybody else think run across yet? Okay. On that same problem? Yeah, that was those two. So if you come in on the side with the infinite oscillation, right, then the limit's not going to exist because it's bouncing back. But when you come in from the other side, when you come in from the right side, you can tell where it would be, right? It would be at 3 on this. It sounds like that's one we need to talk about. One like that. Uh-huh. Don't know how. Okay, all right, so let's look at this one. So, x squared minus 8. My short-term memory is garbage, so bear with me. X squared minus 6. That one was, the limit is 6, 2, 0, 8. 8 from there. Yeah, definitely factoring. Good way to simplify what we're looking at. You could you? You factoring is a good way to go. So we've got a common factor of x and on mine minus 8. On the bottom, factoring that trinomial. Let's see, we need factors of 64 that give us 60. See those jumping down? Oh yeah, 8 and 8, yeah. That'll work. Ain't easy. Then we get a cancellation. Yeah, so we're coming in numbers from the right of 8, so bigger than 8. So like here we can just do a little scratch work, you can do a little calculator work. So like if we try 9, have 9 over 9 minus 8, so that's If we do 8 point, so let's try 8.5, so getting a little closer. Have 8.5 over 8.5 minus 8, so 0.5, which is 17. Mine's probably, I bet yours is coming from the other direction. Yeah, so yours probably, yeah. But the idea, we can try a few numbers, right, that are approaching that way, get an idea of the sign. So as you see here, as the x values are getting smaller, and the functional values are getting bigger. And it'll just keep doing that. And then the thing that's different between mine and yours probably is the sign. So mine, I'm getting positive values out. They're getting bigger and bigger and bigger, so that's tracking toward positive infinity. If you had a minus sign, like if it was negative x on the top, it would be making all these negatives, so you'd be getting large negative values. You can just try a couple, 2 or 3 test values. Idea. Have another one? That's good stuff. So that's all on web assigned for now. I've got a few more examples for us to do from last section. Did some Friday. What section? 2.3, the using the limit laws. So let's look at a couple more examples. This one is the same idea as ones we've already done. Maybe the algebra is a little bit of something we might want to review, so I picked it. 2x squared plus 3x plus 1 over squared minus 2. We're looking at the limit as x approaches negative 1. Always, first thing to try is the easy thing. First thing to try, we can just try direct substitution, where we plug in negative 1 for x. On the bottom, if we try that, negative 1 squared will be positive 1, and negative 2 times negative 1 will be plus 2. And we got minus 3, so we end up getting 0 on the bottom. So direct substitution is going to let us down. And what's our next try? Do you remember if direct substitution gives us 0 in the denominator, then need to try to rewrite it somehow so that we don't have that 0 in the denominator equation. Ooh. What can we do? Do some algebra. Factor. Pick this one because the top's a tougher to factor. Not much. The bottom's not bad. Because we've got a 1 leading coefficient on that one. So we need factors of negative 3 that add up to negative 2 plus 1. Thing I thought we might need to review a little bit is factoring trinomials when our leading coefficient is not 1. So that's going to take me a little bit of room. Off to the side. Sometimes you can guess and check, right? You can get lucky. Not have to do too much work on this. I want to show you my version of what to do if you're stuck and can't see it. So there's a bunch of different methods people use to factor these. Got a way you like to do, use it. That's fine. I'm going to show you one particular method. I just like this one because there's no guessing. So when I'm saying guessing, what you could do, right? You could write down your parentheses. Say I know my first coefficients have to be factors of 2. My last coefficients have to be factors of 1, and I got to pick them correctly, so I get 3 in the middle, positive 3. And this one's not too bad to do that way because the only choices for factors of 2 are 1 and 2. Factors of 1. If you have bigger numbers, more factors, then it might take you several guesses and then doing FOIL to check it. So, way to go about these, if you can't see them right away, is take the first and the last terms, multiply those together, 2x squared. And we want factors of 2x squared to add together and give us the middle term. Again, that's not too bad to come up with because we don't have many choices. That's usually the harder part, finding those. Here, and what I do, this is where it goes different for a lot of people, a lot of different techniques. What I do is I rewrite the middle. Instead of writing it as plus 3x, I write it as my two new terms, so plus 1x plus 2x plus 1. Then I factor by grouping. First two, last two. There, we've got an x in common in the first group. X in common in the first group. Leaves us 2x plus 1. And we can just factor a 1 out of the second group. Get down to the final answer. Now I've got a common factor of 2x plus 1. Factor out 2x plus 1 from the whole thing. That leaves me with x plus 1. Again, if that's confusing to you and you've got some other way that you like factoring, fine. Thought I would show you that method. Then factor 2x plus 1, x plus 1. Got what we wanted to happen. Plus 1s cancel out. That has solved our 0 in the denominator problem. Now we can just use direct substitution. Or a little arithmetic. Negative 2 plus 1 is negative 1. 4. So all that scratch work was just factoring the top. On that particular one, guessing and checking is faster because you don't have many choices for the numbers. Bigger numbers that can be. Anybody learn it that way? Not really? Okay, so something new. Questions? Anybody that wants to know, did you follow what we're on factoring? Figure out the middle and then factor by. Kind of not. Looks a little different. Looks like one you got in the homework. Limit is h approaches 0. Negative 5 plus h squared minus 25. I recognize what this thing we're taking the limit of is from algebra class. Yeah, well, yeah, this one particular difference quotient had a mean slash good algebra quotient. So thing's gonna stick around. We'll see it again. So the issue right away, just trying to find the limit of this thing. Again, same story we've been dealing with. If we try direct substitution, we've got 0 in the denominator. That's not going to work for us. Some way to rewrite this thing algebraically so we don't have to 0 in the denominator. So this one factoring, I guess maybe you could. Thinking about it like different. It's something interesting to try, but what else can we do to try to get some cancellation? Squared here. You can multiply that out. So that's, you're doing that the long way. Negative 5 plus h times negative 5 plus h, FOIL method. You can shortcut the FOIL method here. Negative 5 squared is 25. And you know the shortcut for squaring binomial? It'll be helpful. So you square the first term, and you multiply them together. Negative 5h, double that, negative 10h, that gives you the middle term. Square the last term. Do FOIL. End up with the same thing, you just have one more step, you have to combine like terms of it. That multiplied out. Anything useful that comes out of that? One thing kind of jumps out. What goes away? Yeah, 25 minus 25. Away. And our goal, trying to get rid of that h denominator. Any way we can make that happen? Yeah, factor out an h, because we've got an h in common now with everything in the top. So good. Factor out an h in the top. Negative 10 plus h over h. Factored out h and h in the denominator cancel. Direct substitution. Negative 10 plus 0. Something else to look for. Huh? Another one. Oh, I got h approaching 0 again. We got square root of 9 plus 8. Also does one. A little tricky. Okay, so square. So the issue here, we don't have an equation to like square both sides. We can square top and bottom. Square top and bottom. But if we do that, we're squaring our function. Not real. Maybe not 100% sure that doesn't. And then actually, if you square the bottom, you just get h squared. Plug in z. So you're on the right thought path. For 3. That's a good thinking too, because h is supposed to be close to 0, so square root of 9 plus 8. I'm not quite sure how to make that work algebraically, factoring it out of 9. Good thought. Good. What do you do if you're trying to get rid of a radical? If you have some expression and it has a radical in it, and you get a radical. Yeah, that's that changes it to the 1/2 power gang. I'm thinking more along the lines of, let's just, if you got like 1 over square root of 3 and you don't want a radical on the denominator. Yeah, we multiply by, remember? At root 3 over root 3. Because we're not changing the value there, because that's just a fancy version of 1. Radical. What if it was? Had something like that, we wanted to get rid of the radical on that one. I don't think we've done one. You're probably thinking about the right thing. The name is not. So what can we multiply by? Multiply by almost the denominator. So we change something. Flip the sign in between. Called the conjugate. Yeah, I thought that's what you were thinking. The reason why that works on top, that one's no big deal, right? It's just the bottom is really what we're interested in this example. The reason why that works, this thing is in this pattern, a minus b, a plus b. Multiply those together, you'll get squared plus b squared. Squaring those, we don't have any square roots left. Radicals. You could do FOIL method. This is a long way of getting it. It's also 1 squared to 2 squared. 3. Radical in the bottom. That's some algebraic manipulation we can do anytime we have a radical involved. Hopefully I'm not wrong. I haven't worked it yet. I think we can multiply by the conjugate at the top. This one. Get what we want. So we just want the denominator not to be 0 if we do direct substitution. So let's try that out. Multiply by 9, square root of 9 plus h plus 3. Square root of 9 plus h. Top. We'll get the first thing squared. Plus second term squared. What do we get on the bottom? Do we get anything that helps us? No. So maybe I picked the wrong technique. Not helpful, not helpful. Okay, so I picked in my mind when I looked at this, picked the wrong technique. So, because if we plug in 0, we still get 0 times something. So here's the part where calculus class gets real a little bit. You pick the wrong technique, you just get garbage, and you have to go back and try something else. I borderline my teaching style. I try to find a balance between being real with you about how it works, like how real people do calculus. Try something and it doesn't work, and you try something else, and wasting your time. I don't intend to waste your time, but I do want you to I don't want you to feel like everybody just automatically knows what technique. That is not how mathematics. The way mathematics is done is you mess up so much you run out of mess ups and you do the right thing. I may have to kind of drawing a blank on that one. Good. Okay. Table that one for the moment, so you don't have to sit here and watch me think so much. If it comes to me in the back of my mind during class, well, not I will do. You have one more than I for sure know how to do. This one can look weird if you don't remember all the different theorems that we. It's actually an easy problem. We got this situation that 2x is less than or g of x is fourth minus all x. If that's true, evaluate, find the answer to. Limit as x approaches 1 g of x. So if you don't remember all the theorems we had, that might be mind-blowing. Like you don't even tell us what g of x is. How are we supposed to know what the that theorem we had right at the end? called the squeeze theorem. It says if we have a function that we know is between other functions everywhere, or at least around the place where we're trying to find the limit, then if the limit of the smaller function and the limit of the bigger function are the same, the limit of the middle function has to also be. So really we're just checking two other limits on this one. Checking the limits of the smaller function and the limit of the bigger function. We want the limit as x approaches 1, 2x, smaller function. That one we can just use direct substitution. 2. Then we want to check the limit as x approaches 1 of the bigger function. Turns out they're the same, we can use the squeeze theorem. If we try direct substitution over here, 1 to the 4th squared 2. That's 1, yeah. Minus 1. Oh yeah, so 2 is what we want. Looked at the wrong thing, I was panicking. They're both 2. So since the limit of the smaller function is 2, the limit of the bigger function is 2, the limit of the one in the middle has to be it's like the picture is we're squeezing it from the top and the bottom. And so if we take our middle function and we squeeze it between two functions that have the same limit, there's no choice for the middle function except that. It doesn't have anywhere else it can. Yeah, so it's more kind of a top and bottom, approaching from top, approaching from the bottom. It would be for us, yeah. Oh, if it didn't have less than or equal, just let's double check. Let's look at the theorem. I think okay. Less than or equal. Well, there may be, probably has some cases where if it was strictly less than, still works, right? Because if you know one's strictly less than, one's strictly greater than, the limit could still be right there. Limit could match. But yeah, the theorem does have the or equal to. Strictly less than is not required. That's a good question. Here's the picture for. So we remember we got one that's always smaller, or it could be equal. We got one that's always bigger, or it could be equal. So if those limits are the same, then one in the middle smushed. It doesn't have anywhere it can be except for at that same number. Right? Questions on? That's like the. I think that's like the last number 12 in that. Yeah, number 12 in that homework. I'm going to start on 2.5. It's going to take us a little bit here, so We won't finish this section today. There's be a lot to talk about. We're going to talk about this property of functions called continuity. We've actually already seen a little brief mention of continuity. We said that direct substitution property we had in the last section, that if the limit as x approaches a of a function f of a is the same thing as the limit x approaches a of f x, and said that was continuous. So that is our definition, but we're going to see that there is a little bit more implied in that statement than you might about. Things we want to check. It is worth it for us to talk about continuous functions because continuous functions have very nice properties all around, but especially when we're dealing with limits. Other calculus ideas, continuity is a very nice property to have. If we're guaranteed that a function has continuity, then it makes a lot of other things easier. We want to be able to identify continuous functions. Our definition we've actually already run into. That function is continuous at some number that we're calling a if the limit of that function as it approaches a is the same thing we get when we use direct substitution when we evaluate the function number a. Say that function is continuous at a. So really there's some other pieces that are implied there. It's a nice simple compact continuous at a if the limit as x approaches a is f of a. Really we kind of have three pieces going on there. That statement, number one, we have an assumption we're making. That's that the function is defined at a. F of a exists. If a function that's not defined at a, then we don't have continuity. Two, that the limit as x approaches a exists. Limit as x approaches a does not exist, then we can't have that. Number three, that the two things match. Limit as x approaches a, thing we get when we evaluate the function at a, that number. Parts of this I'll come back to. Looking at the compact form here. Right? So number one says in order for this to be true, this number on this side has to exist. Or in other words, the function has to be defined at a. Number two says in order for this statement to be there to be true, that the limit as x approaches a has to exist. This side doesn't exist, we can't have this. Then number three says it more like this. Limit and the function continuity. Longer version. We need all three things. Another way you can think about what telling us that thinking about how when we change our x values, what happens to our f of x values. So another thing this is telling us, right, another way of thinking about it is that if our x values change very little, have a small change in x, then we have a small change in f of x. Probably easier to think about that the other way around. If we had a function where a little change in x made a big change in f of x, that would not be continuous. We'll look at the graph. Continuous function. We have some a value where a function is not continuous. We can say that where that property does not hold, we can say that our function f is discontinuous at a, or probably the one you'll see more often, that our function f has a discontinuity at the number a. So let's think about the graph of continuous function geometrically for a second, and then we'll come back and we have a really plain English description of what it means for a function to be continuous. And put your pencil down on the paper. Draw the graph without picking your pencil up. Continuous. Continuity. Anywhere you have to pick your pencil up would be a discontinuity. So it's kind of what the name implies, right? Continuous, like you can continuously draw the graph without having to stop and pick. Back one slide here. A lot of functions that describe things that go on in the physical world turn out to be continuous. So if you think about driving in your car, so start driving at time 0 and you drive for 4 seconds and stop, and between time 0 and 4, that is a continuous function because at any point in time, have a nice smooth graph, right? Like you're located from here and you could drag your pencil with the car even, drag it to here and you don't have to pick it up anymore. So what I'm saying there, we don't have anywhere when you're driving in your car that it teleports yet. I don't have any way I can be standing over here and then teleport to the other side of the room. I have to actually walk over there, so I've got this smooth motion through time over to the other side of the room. Drawing that on the graph, we don't have to pick our pencil up. So lots of physical phenomena are continuous. You can think about temperature change. As the temperature increases, it does that smoothly, or at least there's not any gaps in there. About a certain time, you don't go from time 1, our temperature is 15 degrees, and then at time 1.001 seconds, our temperature is 75 degrees. I mean, crazy jump. Temperature over time would be in that example of continuity, but continuous one. Then it says we do have examples of discontinuities. It says think about like electric circuits. Depends on how much you're into electricity. Maybe you're knowledgeable, some of you're not in it. But think about, so right now we've got this light on because we've got current flowing through the light bulb. We track how that current flows over time. Do that, that's not a smooth current flow anymore. So now we've gone to 0, probably close to 0. And now it's back on. So we've got it's not smooth in that case. Got the jumps. One of the things we are avoiding when we're talking about continuity. Jump would be discontinuity. So let's look at a couple graphs. Here's a graph. Got some function f. Have some discontinuities here. Again, you can think about where you would have to pick your pencil up to draw the graph. So if I'm tracing the graph, it's okay to start over here on the left of the domain that we have. That's all smooth. We're good. I don't have to pick my pencil up. But then what happens at x equals 1? We've got a hole there. So we can't just draw through that. We would have to pick that up and then start back right after 1. Go down to x equals 3. If we wanted to keep going from there, we'd have to pick our pencil up to go back up to the top. And have to pick my pencil up. So I have discontinuities at x equals 1, 3, 5. Discontinuity. And those are 2 of the 3 types we're going. So here, say we have a hole in the graph. Our function is not defined for x equals 1. Got a hole there. At x equals 3, we would call this a jump. Jumping from that y value down below the x-axis to a y value up above the x-axis, right? We just have a gap there. Jump. At x equals 5, we also have a hole, but it's a slightly different situation. At x equals 1, we just have a hole because our function is not defined there. At x equals 5, we have a hole in our graph, not because the function is not defined there. It is defined there. But what's wrong if you think back to our properties we have to have for continuity? Yeah, you're on the right track there. So our function is defined there, but it's not, the function value is not the same as the limit. Because the limit would be down here where the hole is, our function value is up there, point is. So on the first one, x equals 1, our function is not defined there. Discontinuity breaks that rule that our function has to be defined. At x equals 3, what's going on with the limit, the two-sided limit? What's our two-sided limit at x equals 3? Coming down here from the left, up here from the right. Don't match, so the two-sided limit does not exist. So it fails continuity there. And then the last one, the limit does not match the function. Fails continuity. That's property number 1 failing, property number 2 failing, property number continuity. We said all that. Look at some more functions. Want to think about where we would have discontinuities. Think of any x value where our function would not be continuous. So it could be any of the 3 things, right? Either be our function's undefined, our limit doesn't exist at a certain x value, or the limit, the function value do not match. See any potential problem x values there? 2. Yeah, we got a discontinuity at x equals 2. Can't have x equals 2 because our function's undefined at 2. So we have our function's discontinuous at 2. Function's undefined there. The solution down there gives away a little preview of something we're going to learn here. It says that's actually the only discontinuity, and then we can be sure of that. What about B? B got 1 over x squared if x is not equal to 0. Our function value is 1 if x does equal 0. Remember what the graph of 1 over x squared looks like? Squared, so if we put in negative values, it's get positive function values. It looks like. So, and then at x equals 1, now at x equals 0, it says the function value is 1. So, see any discontinuities? For drawing the graph, what x value would make you pick up your pencil? 0. And we've really got 2 reasons. One is because we've got that vertical asymptote, 0. So we would have to, when we got to the y-axis, we would have to pick our pencil up to pick back up on the other side of the y-axis. And also, we would have to pick our pencil up to draw on this point that does not match. That on C. We know we would have a discontinuity at x equals 2, but things saying forget x equals 2 on that part. If x equals 2, we'll just call it 1. How can we check if we? What do we need? We need the limit to exist, function, or the function to be defined. This one's defined for all x. We need the limit to exist. And okay, so we could find the limit of this, right? It's a rational function. Find the limit. And we can find the limit of a constant. Find the limit of both of these. And the last part, we need the 2 values to match. So if we wanted to find the limit of this thing, x squared minus x minus 2 over x minus 2, we could factor the top and the bottom. Cancellation. Then if we plug in 2, that's what x value we're looking at around. Get limit would be. But on C part, f of 2 is 1. So match. Hanging in there. Kind of lecture heavy right now. Hold on. What about D? D is a weird function you might not be familiar with. C is the greatest integer function. Weird brackets. It's too small for you to see. They're brackets like so this function returns next integer. So I could plug in 1 for x, you get 1. Plug in 1.1, 1. You get the greatest integer less than or equal to the value. Plug in 1.5, you get 1. Plug in 1.9, you get 1. Plug in 2, you get 2. Anybody seen that function before? Greatest integer? No. So here, let's look at the graph of it. It gets brought up in examples quite a bit. Here's what the graph of the greatest integer function looks like. So it returns integer that is less than or the biggest integer that is less than or equal to the x value. So when we plug in anything between 0 and 1, we get 0. When we plug in anything between 1 and 2, we get 1. Plug in anything between 2 and 3, we get 2. Got this staircase. Okay. So where is it going to have discontinuities? Yeah, what kind of number? Yeah, and the negatives too, so every integer. So we got continuities at 0, plus or minus 1, plus or minus 2, plus or minus 3, plus. So here are the graphs on A part. We just had a hole. B part we had where the function value does not match the limit. C part we had a hole, but it was redefined at another number, but then the limits don't match. The limit and the function value don't match. And we had that weird function. Had all those. So let me just put these in categories for you, okay, and then we'll stop here. Now, there's a lot to try to absorb in the memory for. So when we have a hole, the more formal name for that, the removable discontinuity. So that's like graphs A and C. A, we just have the one hole and that's all. C, situation where we have the hole, but point for that x value is redefined at another y value. So those two we call removable discontinuity. This one's removable. Sorry, C part, removable. And the reason why we give them that name is that we're saying we could get rid of the discontinuity if we just redefined one point. So on C part there, all we would have to do is we would redefine when x equals 2, we just make it match up with the rest of the graph. Our discontinuity would be. And on A part, we have a hole, so we just say, well, okay, at x equals 2, we'll give it this value. And our discontinuity. So if you have a single point like that, or if you just redefine one single point, get rid of the discontinuity, that's called removable discontinuity. D part, we've already seen, call that a jump discontinuity. Jump from, we have a gap in our y values. On these, we actually have lots of jumps. Right? We have a jump at every integer. And B part, we actually call an infinite discontinuity. That's a little bit deceptive because on that one, we said the limit and the function value didn't match. Really what's causing the big picture here, you could ignore this point and it would still have a discontinuity there because thinking about our limits, we have the idea of an infinite limit. And we can say the two-sided limit of something is infinity, but that's not really a number. So there's no way our function value could match. Our function value is going to give us a y value, a number. So anytime we have a vertical asymptote like that where our values are running off to infinity, then we're going to have a discontinuity there, and we call that an infinite. Okay, you did good hanging in there. All right, you did good hanging in there. We'll stop there, and we'll pick back up there on Wednesday. And so no new assignment due yet. I've got it set for Wednesday, assuming we get finished with this section Wednesday. I'll move it.